Thank you very much, Eva, and thank you very much for inviting me to the seminar. It's great. It's almost as good as being in Boston, but maybe sometime in the future soon. As Eva said, I'm going to talk about cactus groups and cell modules, and I have two aims that I want to get across in this talk. So I understand that the seminar is a little bit varied in terms of the areas people are coming from. So I want to the first aim is just to tell you what a cactus group is and maybe why one should care about it. So hopefully that's one takeaway for you. And then maybe for people who have slightly more expertise in representation theory, I want to tell you a little bit about where I think the cactus group might be useful and where to look for uses of the cactus group. So the cactus group has appeared in several areas, but I don't think it's unfair to say that it hasn't been particularly useful in terms of proving other things yet. It's uncovered a lot of structure, but I think that it remains to be seen how it's going to be useful. Okay, so those are the two aims. I should say this is the first time that I've done a talk off the iPad writing, so hopefully the timing works out. Usually I use slides, but we'll see. But yeah, we have 50 minutes, right?
You have an hour, actually.
Oh, I have an hour. Okay, great. Okay, perfect. Great, that's perfect. Okay, great. So the plan for the talk is just to give you the basic definition of and some motivation a little bit about where the cactus group comes from. I'm going to tell you about Hecke algebras and what cell modules are. So that's just some background. And I'll tell you how this cactus group acts on these cells, and then we'll get to talking about how it acts on cell modules via this thing called Trinfeld's unitarization trick, and then there'll be a very short thing at the end where I give you another little result. So that's basically the plan. So let's jump into it. The first thing I want to do is just I guess set some notation. So we're going to be working with Coxeter groups, and I'm going to be slightly vague.
Is it possible to make it a little bit larger?
Oh, I don't know. I think
That's good. Thank you.
Yeah, I might have to zoom in and out at certain points. But yeah, I think. Oh, you know what? Hang on. What I can probably do. Oh,
That's actually was quite good. Thank you.
That's a house. Oh no. Can you see my screen? Or has it disappeared? Okay.
It's disappeared now, but
okay.
You have to reshare it.
I'm sorry.
Maybe if you have your tablet in the opposite orientation.
Yeah, exactly. That's what I was trying to do, but it seems to have.
Yeah, no worries. I'll pause the recording.
All right. Great. Okay, great. So I just want to kind of set some notation. So we're going to be talking about Coxeter groups. I'll be slightly vague about exactly which Coxeter groups apply. Most of the time we'll be talking about all Coxeter groups, but sometimes we'll want to restrict to finite ones or something sensible. So a Coxeter group is just something that has a presentation like I've written down. In particular, it's generated by involutions, and every pair of involutions has the product of them has some order, fixed order. Okay, and so I mean the obvious or the kind of standard, examples. The first one is the symmetric group, which is generated by the transpositions of neighboring integers. And here the powers of the transpositions. So either they commute, which means that the product has order 2, or neighboring ones, the product of them has order 3. So that would be the Braid relation. And let me just say what I want to say is, well, one thing that we can do is we can write a little diagram, draw a little diagram where we have vertices labeled by the generators, and then we draw an edge between every pair of vertices and label it with a number according to the order of their product. So that means that an edge between these two neighboring transpositions would be labeled 3, which means that they satisfy a braid relation, except if it's 3, then we just, tradition is we don't label it. So these would, the diagram would look like this. And then if you have, so there should be an edge labeled 2 between these two transpositions, except we just don't draw it. So no edge means that they commute. Okay, so that's the idea. So then another example would be the dihedral groups. So dihedral group. Of order 2n, right? So this has 2 generators, both involutions, and their product is order n. And then the diagram would just look like this. Okay, and then I mean you can kind of draw anything you really want. I don't know, something like this. And in this case, you'd have if you label this by 1, 2, 3, 4, 5, then you could have S1 and S4 commute, right? And S2, S3, S2, S3. So the power of S2 times S3 would be 5, and another way to write that, what I actually want to get across here, would be as this. Okay, so 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2 equals 3, 2, 3, 2, 3. Okay, and so on. Okay, fine. And I mean, the other thing I want to say is this diagram has 2 connected components. So that means the generators in both of these connected components commute. And so this Coxeter group would actually be the direct product of the group given by this diagram and the group given by this diagram. Okay, so that will be something that comes up later. Okay. All right, so let me kind of talk a little bit about braid groups and also give you some definitions or some places where the Cactus group appears. All right, so first of all, the braid group. So it has, I mean, maybe the first place it appears, depending on your perspective, is topologically. So if you have a Coxeter group, then often it will have a reflection representation. Okay, and so with this reflection representation, you can take the regular points. And so this means just the reflection representation minus the reflecting hyperplanes. And if you take the quotient by the action of the group, so this is the set of all points where the group acts freely. You take the quotient. The fundamental group of that is the braid group. And so the thing to say here is in type A, you've seen this. So the symmetric group acts on n complex points, and you can take then n complex points minus the big diagonal. So this would be the fancy way to say it would be moduli space of n non-intersecting points. And if you quotient this by the symmetric group and take the fundamental group, that this is the usual braid group that you, the Artin braid group. Okay. All right, and so the Cactus group also appears topologically, and this is how it first appeared. And so there's a kind of a procedure that you use to get from the braid group to the Cactus group. So what you do is you look at the reflection representation. So here we have the regular points, the reflection representation, and you take its projectivization, you compactify. So this is the De Concini Procesi compactification. And you do a similar process. So you take the quotient with respect to the Coxeter group, and you take the fundamental group. So there's 2 important things that I have to note here. So first of all, okay, so this is not so important. You have to take this quotient stack. Okay, whatever, that doesn't matter. It just means you have to take a sensible quotient. But you have to take the real points. So the process here was to get from the Braid group to the Coxeter group was to compactify and take the real points. Okay, and so this is somehow important. And let me just spell out what this is in type A. So type A, you have that this reflection representation, this is the moduli space of n+1 points on P1. And then the compactified version is what's usually written M0 n+1 bar, which is the moduli space of n+1 of stable, I should say, stable n+1 pointed genus 0 curves. Okay, so I mean, this is a very classical algebraic variety that comes up all the time. Okay. What did I want to say? Let's see. Okay, and so maybe I can just say, tell you why this is called the Cactus Group now. So an element of this, or a point in this moduli space, what does it look like? Well, a genus 0 stable curve with n+1 mark points looks something like this, right? You have it's genus 0, so it's a chain of P1s. And then you have to have points on here, and they kind of arranged like this in some way. Okay, so it looks like a cactus. If you've ever been to Arizona or California, this is maybe familiar. Okay. All right, so let's go down slightly. Are there any questions before I move on?
Just very quickly.
Yep.
So the projectivization of Hreg, this is one of the wonderful compactifications.
This is the one that is, yeah. So people get confused if I call it the wonderful compactification. People get confused because there's something to do with the group that's called the wonderful compactification.
Right.
Usually people call this the wonderful model, but it's the same idea, right? You embed it in some projective space and it's a blow up along a series of hyperplanes.
Okay, I'm sort of accustomed to seeing it if there's some like ambient algebraic group acting, and then you're compactifying with respect to that action. And that's maybe not what happens here.
I think that I'd have to think about it, but essentially what you're doing is you have this hyperplane arrangement, and you're going to blow up along the intersections of all of these hyperplanes in some specified order, and you get a compactification. Yeah. So I mean, I'd have to think about exactly the relation to what you're saying. I mean, it's called wonderful for some particular reason, presumably. So there's probably a connection. Okay. All right. And so maybe another aim of the talk is to kind of give you a sense that the Cactus Group. Yeah, of course. Yeah,
sorry, no, I just wanted to say, Peter, this compactification is a wonderful model. Is defined very generally for a hyperplane complement. So here we know it's talking about it for a Coxeter arrangement, but you don't need to have any symmetry of the arrangement. You take any hyperplane arrangement, and the Concini-Procesi will produce a model for you, which is something in which the complement of the hyperplane sits with divisor, with a normal crossing divisor.
Yes, you can even do it much more generally if you have some arrangement of subvarieties in a variety. It works extremely generally.
So there's no symmetry assumed here, but because the compactification is functorial, if you have the symmetry, which is certainly the case for the Coxeter arrangement, then the symmetry will act on the model.
Yeah.
Can I ask a quick question? Valerie was saying this is kind of factorial, just depends on the arrangement, but I thought there is also a choice of building set that allows you to do these blow-ups in a specified fashion. And
yes.
Yeah, but
That is a further choice. Okay, that's a further, yeah, that's a further choice. But functorial means with respect to symmetries, and so you'd have symmetries.
Well, that's an important choice, Valerio. You have to make it. You know, it's not God-given. You have to specify which one you pick. Otherwise, you don't have a construction.
Any symmetry of the original arrangement will preserve any choice of building set you make, right?
So, but no, my question is, which one do you pick in order to get this?
Oh, the
specific
minimal,
group?
the minimal one.
If you pick a different one, you'll have a different cactus group.
Yeah, the minimal one. The one
Okay.
of.
All right. Minimal in what order? Brujah order or what?
No, there's no Bruhara. There's a lattice of such things, and you the one that's called itself consists of irreducibles. Anyway, well, let's not get Noah too off. But the one that consists of the building set that consists of irreducible subspaces.
Okay.
Yeah, I mean, I think there are several ways you can blow up, and you get the same thing. Anyway, okay. Okay, so yeah, so another kind of aim of the talk is to kind of convince you that the cactus group seems to always come as from some process applied to the braid group. And this process, hopefully by the end of the talk, you'll be convinced is some kind of asymptotic limit. And so from this picture, I don't know if that's clear, probably not, it's certainly not clear to me. If it's clear from this picture, please explain it to me. But yeah, okay, so let's see some other places that the cactus group pops up, or some actions of the cactus group pops up. So the next is kind of a categorical in nature, so maybe more familiar as well. So if you have a braided monoidal category, so something like the representations of a quantum group, then any object, its n-fold tensor product has a action of the type A braid group. In the same way, you can have, if you have what's called a co-boundary monoidal category. So for example, the category of crystals for Lie algebra, then you get every object on its n-fold tensor product has a action of the type A cactus group. Okay. So that's another place that it pops up. And there's an analog as well for other Coxeter groups. So if you have what's called a Coxeter category, so this is due to Appel and Toledano Loreto, except I can't spell. Okay, then this is kind of an analog where you have the type W Coxeter group acting on every object. And so this kind of corresponds to the internal action that you get from the quantum vowel group. And the picture on this side, well, I mean, I don't know, but I mean, I'm sure there is something there. It's just waiting to be worked out. I guess the only thing missing is some motivation, but I'm sure it exists. And so maybe something a little bit more recent is that if you have a category with a categorical G action, so then using there's always an action of the braid group coming from described by Chuang and Ruquier kind of originally, and so there's a similar picture. Well, so this action happens by perverse equivalences. On the derived category of C. Okay, this induces an action of the cactus group on the set of irreducibles in C. And so this is by Halacheva, Losef, Licata, and Jacobi. Okay. And so then the last kind of place I want to talk about where the cactus group comes from is algebraic. And so I'll give the definition of the cactus.
Can I ask, what is the generality of this result? I mean, for which, so you say any category with a categorical G action has an action of the cactus group on the.
You'll have to ask about exactly.
Sorry, for us it's type AD, cat smoothie, simply laid.
Okay, thank you. simply.
But there's no more restrictive assumption on the category you start from. So you take a category with a categorical G action of G simply laced, and then automatically you have a action of the Cactus Group. Is that right?
Yeah.
Okay.
That's right. By these Ricard complexes. Yeah.
Yes, exactly.
Okay.
Yeah, exactly. That's exactly what I was looking for. And so maybe I should also say that there's something else as well happening back up here in topological land. So there's the action of the braid. There are actions of braid groups. So here I showed you that the braid group is appearing as a fundamental group, and so you do get actions of braid groups by monodromy of quantum differential equations. So this is, so for example, the KZ equation. And so, I mean, here you can look at work of Kunkov, Bess, Kafnikov. Okay, and more people. And there's an idea that this, and it's worked out in some cases, that this should appear, this should give you Cactus Group actions, kind of as the asymptotics of this, of the monodromy of these differential equations, in some precise sense. Okay. Except
that the QD that you just mentioned are actually trigonometric, so they tend to give rise to monodromy actions of affine break groups, not finite break groups.
Right, exactly. But you can take the degeneration to the rational.
So you might as well start with rational type differential equations, such as the
right. Okay. Yes. You're right. Yes. Yeah. Exactly. No, I'm just trying to indicate that there's a larger picture. And I guess, I mean, from these affine braid groups, you would still expect some kind of Cactus Group action.
But affine cactus or finite cactus?
For the cactus of the affine Bar group would be my guess. But I mean, I don't know. This is something that you would really have to speak to Besrakhovnikov about, I guess. But there is a nice picture, and I guess the other reason to mention this is that here the braid groups that are appearing are not just braid groups of Coxeter groups; they're braid groups of well, they can be all kinds of braid groups, and so you get Cactus groups that we haven't really met yet either. Okay. In any case, let me
just to comment this picture. I mean, this picture can be made a little bit more precise in the rational case. I mean, so there are monodromy actions of these Coxeter groups coming from the Casimir connection, and the limiting picture, I mean, at least has been worked out by Eva and Joel Kamnitzer and collaborators.
Yes.
That this arrow is a dashed arrow, so it's morally a limiting picture. They worked out the picture precisely. There is a monodromy picture, and then the limiting picture is a dashed arrow. But I mean, it's
yes, exactly. And then there's a connection between these two pictures that tells you that these, just like there's a picture, there's an arrow between.
Oh yeah, that one is not dotted actually. That's part of what Eva, Joel, and
yes.
And others worked out. So that's that one on the right is not dashed. It's a solid arrow.
Okay. All right. Okay. So okay, but let me tell you maybe a little bit more precisely exactly what the Cactus Group is. So hopefully this will be a little bit more acceptable to people who want definitions. Okay, so first of all, what is the braid group? So the braid group has a presentation like this. It's got a generator for every element for every generator of the Coxeter group, and the relations are simply the relations of the Coxeter group, except we forget the fact that the generators are involution. So you just have the braid relation. So this would be MST factors, and the same here. Okay, and then we have the elements TW for W in the Coxeter group, where we'll write this as TS1, TS2, if you can write W in some reduced way in terms of these generators. Okay. And so what is the Cactus group? So it's going to be similar, except instead of starting with a generator for every generator of the Coxeter group, we're going to start with subsets of the generators. And specifically, we're going to have a generator for every subset of the generators, such that the parabolic subgroup is finite. So this is the parabolic subgroup. And so all this means is that you take the subgroup generated by the elements in I. Okay, and so what are the relations? Well, we want these things to be involutions. We want them to commute if I and J don't interact. And so what that means is that the parabolic subgroup is just a product or isomorphic to the product of these two parabolic subgroups. And the way you can think about it is that I and J correspond to disjoint pieces in the Dinkin diagram. And then there's one more relation that tells you what happens if J is a subset of I. And so in this case, you can commute them, but at the cost of conjugating every element of J by Wi, where Wi is the longest element of the parabolic. Okay, and so this is where we really require that, that we only take parabolics that are finite. Okay, and so what I'm going to explain to you now is that, I mean, kind of a silly statement is that the Braid group acts on the Hecke algebra. The Hecke algebra is a quotient of the group algebra of the Braid group. We'll see that in a moment. And that this produces an action of the Cactus group on the Coxeter group itself. Okay. So let's jump into that, unless there are questions. Nope. Okay. So to tell you what a Hecke algebra is, just very briefly, so there's some parameters involved. So we choose a parameter for every generator of our Coxeter group, and in such a way that if two generators are conjugate, that they have the same parameter. So in type A, for example, all the generators are conjugate, all the transpositions are conjugate. So there's only one parameter allowed to be chosen. It essentially doesn't matter. And so now we're going to define the Hecke algebra. So this is the Hecke algebra, I should say. I'm going to define it as an algebra over rational functions in a variable v. So this can be done integrally, but it'll be useful later for me not to have to adjust my coefficients. And I'll tell you where that's important. It's only really important in one place. But in any case, it's an algebra with coefficients, rational functions in v, generated by, I'll use the same symbols as the generators of the Braid group, so TS, and again, it has this same Braid relation, and then we have one more relation, which is deforming the relation that these things should be involution. So if I was in the group algebra, I would write this, and that would just give me the group algebra. So instead, I can write this, and another way to write this is to say, well, I could write this, and okay, so here you can just see we've added a v instead of this one. And so if we set the L's, all the parameters equal to 0, that gets us back the group algebra. So it's a deformation of the group algebra. Okay. And if W equals some reduced expression in the generators, then we'll let TW be the product of these things. And then these form a basis, right? This is usually called the standard basis. Okay, so this is the Hecke algebra. Okay, and the Braid group just acts by multiplication. Okay, so now I need to tell you what cells are. And so this is, we'll say something a little bit general here. So I can formulate this for any algebra A. And so maybe I think that's going to be a little bit clearer than doing things specifically. So basically the idea is that you have an algebra A and you have some basis labeled by some set X, and you want to construct representations for it. So this is going to be a procedure for constructing representations of your favorite algebra. So with your basis, what you do is you define three orders, or one of these three orders. So you define a left order. So X is less than or equal to Y in the left order. So these are elements of X. If the basis element Cx appears in the expansion of A times Cy for some element in your algebra. Okay, so it's basically you take the basis element corresponding to Y, you hit it with everything in A on the left, so you're taking the left ideal generated by it, and look at what basis elements appear. Okay, and so actually here you need to take the transitive closure. But let's not worry too much. Okay, and so here you can, for the right order, you do the same thing, except you look at the right ideal generated by this element. And for the two-sided order, this is true if X is less than or equal to in either order, X1 is less than or equal to X2 in either order. It's the union of these two orders. So I'll just write question mark to symbolize either order. Okay. All right, and so then the left, right, or two-sided cells are just the equivalence classes in these orders. And okay, I'm gonna do an example to clarify this in a second if you haven't seen it. That'll hopefully make it clear. Now the point that I want to get across here is that if you do take a cell, so you take an equivalence class of one of these orders, so let's say the left order. So if it's a left cell, then you can define the following ideals. So you have this ideal, A less than or equal to C, and that's just the span of the basis elements that are less than or equal to C in this left order. And so that's an ideal because if you multiply the basis element Cx on the left, you're only going to get things smaller in the left order by definition. Okay, and you can define similar ideals. You can have the strictly less than things. You can have, if C was a right cell, you could have the right ideal, or you could have the two-sided ideal if it was a two-sided cell. Okay?
Sorry, no, I
yes.
have a stupid question. You're talking about equivalence. I'm confused about a really basic point. You're talking about equivalence classes, but you didn't define equivalence relation. You defined an order.
Yes, so it's a pre-order. Yes, exactly. I should say this as well. That is unclear. So we say X is equivalent to Y in the left relation if X is smaller than or equal to Y in the left order and Y is smaller than or equal to X in the left order. Thank you.
Okay.
So for this pre-order, it's just the equivalence relation it generates. Thank you. Okay, and so because these are left ideals, they're contained in each other. We can take the quotient and we get a module. So and this we call the left cell module corresponding to C. So this is a left module for A. Okay, so this is just a way to generate a bunch of representations. So let me quickly do some examples. So let's look at, first of all, the example of n by n matrices. And so here we have that we're going to use the basis, just the standard matrix units. And so X is just going to be pairs I, J, where I and J are between 1 and n. Okay, and so what are we looking at? Well, we want to look at a matrix unit. We want to look at another matrix. We want to multiply it on the left and see what we get. Well, what do we get? Well, we get basically the zero matrix plus the jth column of M. And so this basically tells you that the only things that are going to appear are matrix units in the same column. Okay, and so this tells you that, well, two of these pairs are going to be left equivalent if and only if L equals J. So the cells are basically the columns of the matrix. Okay, and if you take the right order, you get the rows. If you take the two-sided order, you get just a single big cell. Okay, but what does this mean? This means that the cell module corresponding to this is just going to be basically spanned by a single column. So it's going to be the span of EKI for K equals 1 to N. And so this is an irreducible left module for this algebra. And so I know this is a silly example, but what have we done? Our basis has given us all of the irreducible modules for this algebra, right? Okay, it happens there's only one irreducible up to isomorphism, but fine. We've produced all of the irreducibles. So let me give you another example. Let's look at the group algebra for a finite group. And so then our combinatorial sets labeling our basis is just the group itself. And then so for if we take any pair of elements G and H in G, then of course there's another element in the group that moves us from G to H. So that tells us that H is less than in the left order to G, and G, of course, is an element that moves us from G to H. Right? The action on G on itself is transitive. Okay. And so what this tells us is that there is a single left cell. Okay. And that this single left cell is just G and it equals a whole algebra. Okay. And so this hasn't told us anything, right? It hasn't produced us any interesting representations beyond the regular representation, which we presumably already knew about since we knew the algebra. So, and you can do this computation at home if you like. If you take the Hecker algebra with the standard basis, this has a single cell. So no interesting representations produced by this process. And so the aim is to find an interesting basis. So that these cell modules actually are new representations and hopefully close to irreducible. And so let me just say very quickly, I mean, there is another obvious basis of this algebra that you could choose. Right, this is a semi-simple algebra, so it's a product of matrix algebras. You could just do what we did before and take the matrix units, and that would produce all of the irreducible representations. But that's kind of cheating because in order to know what the matrix units are, we would need to know the isomorphism that the Artin-Wedderburn theorem tells you about, and that's equivalent to knowing the simple representations. So you really need to work to find a good basis. It's a hard thing in general. Okay, so this is why cells are interesting, I think, for one reason. Okay, and so what is the special basis that we're going to use, or the interesting basis? Well, there's a very special one for the Hecker algebra called the Kasdan-Lustig basis, and I'm not going to define what it is. I'm just going to tell you that it exists and hope that you've heard about it enough that you're convinced that it's something useful. And the cells that we're going to be interested in are the cells with respect to this basis. So these are called the Kasdan-Lustig cells, the Kasdan-Lustig left, right, and two-sided cells. Okay, Are there any questions about cells before I tell you how the Cactus Group comes in? All right. So yeah, so I should say that the causal analytic basis, I mean, one small reason to think that it's interesting, there are many reasons, but is that the cell modules that it produce are in some sense close to irreducible, right? There's lots of cells in a particular, in a given Coxeter group. And why is this even an important problem? Well, if you want to understand the finite, if you want to understand the representations of finite simple groups, then one thing that you're immediately confronted with is determining what these Hecker algebras look like in their representation theory. And I will point out here that it's not just the Hecker algebras that we're talking about in this talk that are important. So also, if you are trying to determine the representation theory of finite simple Lie groups, finite simple groups of Lie type, you come up against Hecker algebras of complex reflection groups, and that's something that's not we're not covering in this talk. And so there's a whole other story about what Kazan-Lustig cells are for complex reflection groups, and that's some motivation, I think, behind studying the Cactus Group and trying to understand it, is a hope that maybe one can use it as an inroad to study complex reflection groups. Okay, so let me tell you how the Cactus Group acts on individual cells and therefore on the whole Coxeter group. So the first important fact that we need to talk about is this theorem of Mathis, and Lustig extended it to the unequal parameter setting. So if you have a finite Coxeter group, there exists an involution on the Coxeter group, so that if you take an element of a cell, a two-sided cell, and you look at the product of the Kazan-Lustig basis element with the standard basis element of the longest element of the Coxeter group, all this does is essentially permute the basis elements. So within a certain cell, you take the Kazan-Lustig basis elements, this multiplication just permutes them up to a very important sign and a power of V. Okay. All right, so what does this do? This gives you an involution on every Coxeter group, on every finite Coxeter group, a single involution. So how does this get upgraded to an action of the Cactus Group? So this induces, so for any Coxeter group W, so now we're no longer restricted to finite ones, a Cactus Group action defined by, oops. So how is it defined? Well, if I take, I take a generator of my Cactus Group and I take an element W that I want to act on. So now W, so one important fact is that W can be written as X times A, where X is in the parabolic corresponding to I. And so there are many ways to factorize a given element in an element of the parabolic and something else. But for Coxeter groups, there's a very special way where you choose this coset representatives to be the minimal length, the minimal length coset representative. Okay, so there's a unique way to factorize this. And so that tells us what we can do is we can look at X. So X exists in this parabolic subgroup. And so we have available to us the involution that Mathis and Lustig defined. And then we can just multiply by A again on the right. Okay, so you're basically just looking at this involution acting on the parabolic part of each permutation. Okay, and so this induces a Cactus Group action. Okay, and maybe a little warning is that it's not true. So something tempting to think about is that if you look at this multiplication, so here we're multiplying a casualistic basis element by the standard basis element for this longest element in the parabolic. It's not true that this just permutes the basis up to signs and powers. That's not true. It's kind of very far from being true. There is a statement that you can make, and I'll very just briefly say it. What one has to do is think about some kind of relative casualistic theory. So you have to talk about relative casualistic cells and relative and the relative version of the equivalence relation, where you think about basically the Hecker algebra as a bimodule over the parabolic subalgebras. That gives you a theory where you can make sense of this. And this is, I've written it as a theorem / conjecture because I think this only depends on, okay, for the experts, I think this only depends on Lustig's 14 or 15 conjectures, but I'm not 100% sure, so I have to chase through exactly what this depends on. Okay, so that's an aside. So okay, so let's talk about examples. So examples of this Cactus Group action. So let me tell you what it is in type A. So in type A, we have a nice description of the symmetric group using the Rsk correspondence. And what this basically does is it says knowing a permutation is the same as knowing a pair of standard tableau. Okay, no, I'm not going to define this, but there's an algorithm that takes a permutation, gives you a pair of standard tableau of the same shape. And so the generators of the symmetric group are labeled by 1 through to n-1. And so let's just take the parabolic for this set. So this would be the parabolic that's permuting the numbers 1 through to q. And then what I will tell you is I won't tell you what sigma I of w is. Instead, I'll tell you what the P symbol, so this is called the P symbol and this is called the Q symbol. I'll tell you what the P symbol of this is. It's just the P symbol of W. And the Q symbol of this is not quite the Q symbol of W. That would just give you something trivial. It permutes, it changes the Q symbol by something called the Schützenberger involution. And it's the Schützenberger involution on the sub-tableau with numbers 1 through to q. So essentially this is, so basically you have a tableau, you look at the first q boxes and you apply this Schützenberger involution. It's some combinatorial involution. It's not so hard to compute. And then this gives you the action of the Cactus Group. And the upside of this is that this tells you that the orbits of the Cactus Group are the left cells. This Cactus Group action is transitive on left cells, so that's quite important. Okay, so here's the dihedral group. So this has 2 generators. This is what a dihedral group looks like. The shaded parts are the left cells, and the Cactus Group action, it fixes, of course it has to fix these 2 things. It has to permute the cells within themselves, and it flips these upside down. So this would be sigma ST. Okay. Okay, that's basically the only thing the Cactus Group does. And so you can see, of course, this has many orbits within each cell, within these bigger cells. Okay. Okay, and so then the other place where this has been worked out is in affine type A. And so there's a similar description of the affine type A group to finite type A, where you have we have an RSK type correspondence, and so she described the cells using a version of this correspondence. And you have some similar picture. I won't describe it, but it's essentially the Schützenberger involution is again giving you the action. And this was worked out by a student of mine, Nathan Chung, who's also applying for PhD positions at the moment. So he's an undergrad at UCLA. So if he applies, you should give his application a look. Okay. All right, great. And so basically, I should also say, like, it hasn't been worked out in basically any other case. I mean, some low rank examples I can do by computer, but it would be interesting to describe this Cactus Group action in other cases. It's a good combinatorial problem. All right, so now let me describe how this action really comes as an asymptotic limit from the Braid group. Are there questions before I start on this section? All right, so let me set up some notation. So the Braid group, of course, if I impose the relation that each generator is an involution, I get a surjection onto the Coxeter group. And so the kernel of this is called the pure Braid group. And so the thing that I want to consider is the unipotent completion of this pure Braid group. Okay, and so what does that, I mean, let me tell you kind of roughly what that is. So basically it's the group-like elements of, you take the group algebra of the pure Braid group and you complete at the augmentation ideal. So the augmentation ideal is the kernel of the map from here to the field where you send a group element to 1. And okay, so you complete along this ideal. And so what does that mean elements in here look like? So this is kind of the important point here, not so much exactly what this is, but if you take an element of the pure Braid group, what do elements of this unipotent completion look like? Well, you're allowed to take power series as long as the power series, the successive terms are within the powers of the augmentation ideal. That's what it means to take the completion. And so, for example, you can take something like g to the power of a -1/2, right? And so why can you do that? Well, this would be the sum as for k bigger than 0 of -1/2, choose n, 1 minus g to the power of k, right? This is just the power series for this function. And so this is something that lives in the unipotent completion, pre-unipotent completion. Okay, so yeah, that's going to be important. And then what we do is we kind of lift this construction to the entire Braid group. We don't take the unipotent completion of the entire Braid group because that doesn't work well. But if we take this semi-direct product with the Braid group and this unipotent completion and quotient out the overlapping bit, essentially the pure Braid group in both, then you get this completion. And so this is, I mean, look, this is not so important. This is basically this is defined so that the quotient of this thing and the unipotent completion of the pure Braid group. So usually if I remove the completions, this is W, right? And so we just still want this to be W. So that's what this definition is doing, that's all. Okay, the important thing is that you're allowed to take power series in the pure Braid group. All right, so here this.
Oh, sorry, no, what is N?
N is K. Thank you. Yes. Let me fix that. Yeah. Okay. So here's the theorem. So this is what I am referring to as Trinfeld's unitarization trick. So what does it say? It says there's a homomorphism from the Cactus Group to this completion of the Braid Group. And how is it defined? Well, you take a generator to this funny thing. So if I take the square of if I take the square of one of these longest elements, I get something that's a pure braid. You can see that in type A easily because basically you're flipping an interval and then you're flipping it again. Okay, so I'm allowed to take this minus a half power and then I multiply it by this standard basis, by this generator again. Okay, and so why is it called Trinfeld's unitarization trick? Because this is essentially due to Trinfeld in type A, so couched in a different way, more complicated way, in fact. Okay, all right, and so there's this homomorphism. So, but what we can do is we can define a composition. So we can go from the Cactus Group to the completion of the Braid Group, and then we can subject onto some completion of the Hecker algebra. Okay, so I'm not going to talk about this completion, but you can believe that this subjects onto some completion of the Hecker algebra. And then we can do the following thing. We can push this generator right through to something I'm going to call xi I, which is exactly this element in this completion of the Hecker algebra. And so now the kind of amazing thing here is that, actually, I was going to do a computation, but let me just skip it. Oh, hang on. No, I forgot where I put this. I didn't actually write this. So the theorem that I need to say here, the kind of amazing thing here is that, in fact, this element, right, a priori lives in some completion, but in fact, it doesn't. It lives in the usual Hecker algebra. And so here, so there's no completion. So that's what this theorem is saying. But working in rational functions is important. So that's where this comes in. All right. And so what this is telling you is that now you can have this element acts on cell modules. So this theorem is basically saying, so the corollary of this theorem is that CW acts linearly on cell modules. Okay, so let me just show you some examples of what these elements look like in type A. I don't know if this will be particularly nice. I mean, I think it would be very interesting to figure out what particularly the denominators are. So the denominators don't vanish. That's kind of, well, that will be, the denominators don't vanish at 0. That's important later. But I don't really know why. So in any case, it would be interesting to kind of have some explanation for the denominators that appear and the numerators. Okay, but let's, okay, so as you can see, they get quite complicated quite quickly.
And this is for the Kazan-Lustig basis?
This is for the standard basis. I wrote one of these for the Kazan-Lustig basis, and I was too lazy to convert the others. But if if you're interested, it's something that I should do. So I'll do it. at some point.
Okay, thanks.
Okay, so yeah, as I said, the main point here is that if you take a two-sided cell, then the Cactus Group acts on this cell module according to a formula like this. So what I'm really saying here is that IE, it matches Bonifay and Losseff's permutation action. But there's extra information. So these linear actions of the Cactus Group carry extra information. And then the final, the only other thing I will say is that we can really make very precise exactly how this is supposed to be an asymptotic limit. Well, we hopefully will be able to make precise, it's still a conjecture, is that if we take, so there's still this extra information, but actually if you take the limit when v goes to 0, you take the limit when v goes to 0, then this action really just reproduces Bonifay and Losseff's action. So in this precise sense, the action of the Cactus Group on the Coxeter group is an asymptotic limit of a Braid group action. Okay, great. So I will stop there. And yeah, if you have questions, feel free to ask.
So can I ask a question?
Yes.
So if I understand correctly, I mean, so part of what you've proved is that somehow you can make the Cactus Group appear before taking a crystal limit.
Yes.
So you respect.
Well, well, I guess this v equals 0 is really the crystal limit.
Yes, I mean morally anyway in some case, but irrespective of this conjecture, I mean, even if it turned out to be false, but you have the Cactus Group appear before you've taken the limit as v tends to 0. Yes. And then your conjecture is that this appearance, which is prior to taking a crystal limit, should be, if the conjecture is true, consistent with the action which is expected or maybe known to exist in the crystal.
Yes. And so a very good question, and I asked this, I asked Tony about this the other day, is whether, I mean, so you have other appearances of Cactus Group actions as some kind of crystal limit. So most interestingly, I think the one that Eva and collaborators have looked at. So here, this is just a permutation action. And so the question is there some Cactus Group acting categorically on, probably it has to be a completion of this derived category. So I think this, so this is, yeah, so yeah, this is something I was hoping to get across, is I would like to really understand to what extent this is a general picture. How often do Braid group actions induce Cactus Group actions, and how often that can they be lifted to linear actions or something more than just something something that's a permutation action?
And so to re-ask the question you just asked, but in a specific but different context. So if I take the Case equation or the Godin model, which of course you know about, so there is a Cactus Group action on beta eigenvectors, as you know, right? But your general statement says that if I take a unipotent local system on, say, configuration space, so something that's, for example, the Casey system, right?
Yes. It
would give me a unipotent local system on the real locus of the wonderful model. So in other words, I'm saying that some of the Case equations should give rise to a Cactus action before I take the crystal limit.
Yeah, I mean, I think so. I hope so. I have no idea how that would.
Well, that's not a hope. It's a fact because of your theorem. The question is then to compute it and describe. Okay. There is definitely you've just shown us that there is a local system on the real points because of that math, right? Because the Casey system is unipotent. I mean, if you say,
oh, I'm sorry, I misunderstood. Yes. Okay. No, I think I understand. I mean, to be honest, I do not understand the connection between this the unipotent completion and the analytic side of the story particularly well. I mean, this is something that I need, and you're telling me that I need to understand it, I think.
Yes, I mean, again, topologically, it's obvious. The question is, right, because if at least if you say the parameter of the KZ equations, you say it's an infinite, it's form a parameter, right? Then it's a clearly unipotent local system. Then the question is, can you compute it? I mean, so can you describe it in a kind of, but in the Betti picture, it's clear that you have a local system, right?
Hi, Noah.
Hi.
That's Matt Hogenkamp.
Oh, hi.
Hey, I have a question. So this is really cool, by the way. I have been needing to listen to you talk about this for a long time. Anyway, so I was curious though. So your theorem with your theorem that you mentioned here at the end was that the square root of t w0 squared is rational, or something of this.
Rational function. Let me. Yeah. So they look like this.
Yeah. Yeah.
Things like that.
So yeah. I guess what if you instead of take the longest element of the parabolic squared, what if you take I don't know, any involution squared, or more generally like TW times TW inverse in the square root of these in the completed deck algebra.
I haven't looked at that. I mean, so you can ask it. You could ask something like, if you take a non-standard parabolic and you take the longest element of that and square it, what happens? You could also ask, I mean, there's also this very interesting case, and this is actually something I've been a bit negligent and haven't done, but there's in type B, there's this fake parabolic that's not really a parabolic, but like you get this A1 times A1. So you can also look at that. Yeah.
Was your theorem for, in what generality was your theorem? Was it, so it was not for all parabolic? Wait, so
it's the standard parabolics. So by standard parabolics, I mean, you have this set of generators, right? But you can also, I mean, like the symmetric group has many sets of generators, right? We've taken the neighboring transpositions, but you could take some other set of transpositions.
I see.
Some other set of n-1 transpositions and get a perfectly good set of generators for the symmetric group. And then you'd have some other standard parabolics, and I guess together they'd all be parabolics. Yeah.
I see.
Some other, yeah.
Cool. But I see. So, but this is cool. So, and your question about having actions of these on derived categories, is this isomorphic to the question of categorifying these in?
I mean, probably. You would expect so.
Yeah.
You would expect that if you had a good notion of categorical action of the Cactus Group, then you would probably understand where it was coming from, and you would. Yeah. The problem is that you're trying to categorify formulas like this.
Yeah.
Right. And so that's. I mean, you understand better than me that that's hard.
Yeah, denominators are hard. Yeah. Anyway, cool. I
mean, another reason that it's hard, maybe I could say. I mean, the other thing I was going to talk about is there's this isomorphism that Lustig defined between the Hecker algebra and the group algebra. So this is something weird, right? The group algebra, the Coxeter group, and the Hecker algebra are isomorphic. They're isomorphic algebras.
Right.
And actually, these elements coming from the Cactus group, they're actually the pullback of the longest element in the group algebra. So if you want to categorify this picture, in some sense, it's categorifying Lustig's isomorphism, which is, I don't know, it's a strange thing to do, probably.
Wait, but how unique is this Lustig isomorphism? I forget. I mean, there certainly are plenty of isomorphisms of that kind, but
yeah, exactly. Yeah. So yeah, that's a good question, right? I mean, the reason that these two are isomorphic is because, I mean, they're two semi-simple algebras with the same numerical data, right? And Artin Wedderburn just says, okay, well, they're the same. but this is a specific one. So how does it work? So you have an isomorphism, first of all, with Lustig's J-ring. So this is supposed to be the asymptotic algebra. So this is, let's say, let me call it something else. B. And so this is an isomorphism. And so this is, I mean, really, what is this? This is just the associated graded with respect to the left-right order. So this gives you a filtration of the Hecker algebra itself. So this is what it is as a module. And then, okay, there's a ring structure on this that I won't talk about. And then this is just equal to H dot 1, the 1 in this J ring. Okay, and so now the isomorphism to the group algebra goes like this. So you can evaluate V at 1, take the inverse. This gives you a map to the group algebra. And it's this composition. Unfortunately, I don't have a better way of thinking about this isomorphism. What I would really like is a better way. But this is the way I understand it at the moment. And yeah, but I mean, I guess this shows you that there's a problem here because the J ring is kind of not at all compatible with parabolics. So if you've ever played around with the J ring, this is something that you would encounter immediately, right? And one appearance of that is that the unit element in the J ring is kind of the most complicated part of it. So this morphism is just not at all compatible with parabolics, which is problematic for the whole story.
Well, actually, you can prove that there is no isomorphism between Hecker algebra and the Val group that is compatible with parabolics.
Right. Okay. Yes. 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 Yes.
So it's not just that this one is bad. They're all from that point.
Yeah. Yeah. Exactly. Yeah. 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 Yeah.
Not possible. So.
Yeah. Yes. But yeah, I don't know what this would, I don't know how you would categorify this, but that's something that you might want to try if you wanted to find a way to categorify the Cactus Group.
I guess I have one more question. Maybe it's brief. You mentioned complex reflection groups. Is there like a similar, I guess I'm not used to thinking with them because there's no like category of circle bimodules there. Yep. But is there a similar story with? No,
and that's something very interesting, right? So one thing that I mentioned before is that in type A, the Cactus Group acts transitively on cells, and that in other types, this doesn't happen. And so, I mean, one thing to say, so actually I wrote a list of questions here. I might as well have these up. So I guess, so one question is can you enlarge the Cactus Group to give you a transitive action on cells? And the answer is, and I mean, the question is, why would you even expect this to be able to be true? And in a sense, this work of Bonifay and Ruquier says that yeah, it should be true, because there actually is a group, happens to be a finite group this time, that does act transitively on cells. And their group, it's defined as a Galois group coming from some ramified covering. But their group does, or conjecturally acts transitively on cells. And their group is defined for complex reflection groups. So the exact relation between Cactus Groups and this Bonifay-Ruquier story isn't clear. except in type A, it's kind of known. But that's really something to work out. And a very related and extremely interesting question is if one can define a Cactus group for complex reflection groups.
Cool.
Any reason, Noah? Do I have any reason to think that the answer is yes in the complex reflection case?
Whether there is a Cactus group, I don't know. I mean, the problem is I don't understand the relationship between the Cactus group and Bonifay and Ruquier's Galois group particularly well.
Oh, I see. So it's because only the definition you originally gave, that one's not going anywhere because it uses real points. So that one's
exactly, yeah, exactly. I mean, but well, no. Actually, this is a good point, right? Let's go back up. So in fact, if you look at the equations defining the hyperplanes for a complex reflection group,
yes,
it's a real equation. It's in fact, it's a rational. It's a finite extension of the rational numbers.
a finite extension, but it's not real, right? No, it's not real. I mean,
there is a real form. There is a real form for the hyperplanes of any complex reflection group. This is a theorem of Bessis, I think. Okay, the problem is that the complex reflection group does not preserve this real form.
Okay, all right, okay.
Yeah, exactly. So you either you have one but not the other.
Right.
And so maybe there's something that you could do there. I did play around with it, and it doesn't seem like you get anything interesting. And really, like the philosophy and these types of things might be that actually what you should be looking for is something more to do with Calogero-Moser space, so some kind of doubled picture. But I don't know. Yeah.
Yeah.
I mean,
is there one example where one knows that there's something that looks like it should be called a Cactus group? I mean,
no, that's the problem. No, I mean, you would think that you can do something very silly, like for cyclic groups, right? You can, right? So there, the hyperplane arrangement is just you just take away one point from the line. So okay, you can blow that up and compactify it, and you just get a line, and you projectivize it to a point, and then I mean, you take the real points of that. It's just, again, it's just a point, so you don't get anything interesting. Yeah, I don't think there's really a sensible guess for what it could be in any situation.
Okay. Any non-real situation.
I mean, well, I do combinatorially, maybe there is one. So one thing that you can think about is this Rsk correspondence. And this exists in some sense for wreath product groups. And this Rsk correspondence, I have a feeling, and I think I should be able to prove that this, what I would call the colored Rsk correspondence. So instead of generating a single tableau, a single P symbol and a single Q symbol, you generate an L tuple of P symbols and an L tuple of Q symbols in some sensible way. I think that this should give you the cells of the wreath product groups when the parameters of the wreath product group are far apart. So this might be called the asymptotic case. I think maybe. And so in that sense, you can imagine that there's some group that's acting by Schützenberger involutions on these L tuples of partitions. And what that would be saying is that really it's just the type A Cactus group that's acting on wreath product groups again. And so maybe the Cactus Group just doesn't see the complex reflections. That's the only sensible thing that I can really think of at the moment.
I see.